Okay, so good morning, everyone. I've chosen to. There's already a typo here. To present you ongoing work with people from University of Western Australia here, my colleagues, and it's about developing some logical formalism to discuss robustness and reliability of systems. So let me just say a bit of things like this. All right, so we will present a logic called robust CTL star. So basically, what the logic does is that it adds some, say, obligatory and robustly operators, where obligatory tells about how the system should behave ideally, and robustly tells that, okay, the property would hold in the current path, but also on deviations of this path, as long as these deviations comes from, let's say, one failure in the system from the current path. This is roughly the idea. So it's a bit, you can think of it as a dual of diagnosis, where diagnosis means that if a failure occurs, somebody expects some property to hold. Whereas robustness concerns, you rather would like the failure not to cause a change of the property, I would say. Or the failure, how can I say? If the failure in the diagnosis causes something, you would like the failure not to cause something for robustness. So it's another approach. So I will give examples, so we may interact a lot on those examples, because they have to be understood and assimilated, so we will take time. It will be fun. And we will see, contrary to duty obligations, among other things. And then I will show you how technically this logic, which seems very, very comfortable, powerful, maybe to express things, which seems to avoid some paradoxes that I'm not very good at paradoxes, because I did computer science, not philosophy. So. But I try to get started with paradoxes, because daily life shows me many things. So then I will show you how to, technically handle this logic, basically. Questions about decidability and model checking and things like that. So the roadmap is first to, of course, introduce you the logic. And the end. So we will have examples, simple properties like bisimulation invariants. And I will just state them. I will not go through all those things. Then we will consider, ways of proving decidability of every CTL star via translations to, settings that are, known as decidable ones. So the first translation will be a translation into quantified CTL star. Fairly easy one, although, much more easy than the other one, actually, where the second goal is to translate this logic into CTL star, and there is a nice way of doing it via an extension of LTL with counter-free automata, operators. So this I'll give you a flavor of it. And I will end with the optimality issues of the translation, basically showing that the translation, there is a blow-up, non-elementary translation from LCTL to CTL star. Notice that it will be a fragment of QCTL star that can be embedded into CTL star, whereas here, in general, you get, the full power of MSO bisimulation invariant properties of mu calculus. But and opacity, I will just tell you the principle of the proof to show that indeed this logic is non-elementary. I don't know how to say that. Non-elementary, more succinct than CTL star. Okay. Questions? No? Right. So we start with very well-known things. We have structures. So think of it as Kripke structures. So we have a set of variables, and we have a valuation of a set of words onto a set of propositions that hold in this word. And the structure is a set of words, an accessibility relation that is, total, serial, you can always go on, and a particular valuation of words in this set of propositional variables. So very simple. Now you have the notion of full path. So W is for words. So, but I've put S here because it's states of systems. I should have put W anyway. So a full path is an infinite sequence in this in the structure. It is serial, so all maximal paths are infinite. And I use notations of this kind because I will call about deviations. So there are some points where the things change. So I need to introduce things like at time I, before I, after I. Very easy. So this is a finite word, and this is an infinite word. And this is a state, or word, so like world. Word, world. Right. So we'll. So what I forgot to say, so here is that because we want to characterize failures, we'll be able to, mark paths or states or words along the paths where some failure occurs. So we'll use variable v, violation, if you like, to explain that, the target of some transition corresponds to an event that is a failure event. So you would call a path failure free if all states are along the path. We don't mind for the first one. The first one doesn't mean, you have no meaning of a failure event. When you start, you didn't have any event, so we don't need to have this. But as long as you start, there is at least one, the state here corresponds to a rich state from the beginning of the path. You would call that path failure free if proposition V doesn't appear at any place. So no event is a failure one, if you like. And we will write failure free paths from W, the set of. So W is a word, right? So you take all paths from W, full paths, and you take those ones that do not hit V, proposition V. Right. And what we call maybe I have put a star, sorry, it doesn't matter. What we call a structure, relevant structure in our setting, would be a structure where, we have at least non-failure. Otherwise, we're not very interested in this. We have trajectories that are, failure-free.
So this is an infinite structure.
Huh?
M is an infinite structure.
It is a structure in this sense. So R is serial. Just go on. You may think of whatever you like, a tree, or.
Is there a finite number of words?
I don't. As I said, a tree. I don't. For the moment, I don't restrict to any particular. I'm not concerned yet with computational aspects of. Okay, now we're coming to the main objects we want to deal with. It's deviations. Right, so you have two paths, and the pi would be an I deviation from sigma if pi would, just be identical to sigma up to moment I. We start with moment 0, if you like, until step I, and then it becomes failure-free. So let me explain. So you have, this is sigma, so switch on. So do you need to, yeah? So which one is it? Because if, so the picture is very simple to understand. Okay, so this is this one, which also would be this one, if it's an I deviation, okay, so this is also pi, all words along. And then sigma would continue like this. And the only thing you know is that you have a deviation here. So this is pi after moment. So didn't I make it right? Okay. After I plus 1. This is sigma after I plus 1. And the only thing you want is that this path, now, this one, is fairly free. What does that mean? Is that here you don't have a violation, you don't have a violation, and so on. So the only place where you may have a violation, say, would be in here. But also, I mean, sigma can be a deviation of itself. Okay? So when you talk about deviation, what are they? They are just either the path itself or a path where only one possible, I don't know if V is true here or not. V may be true or false here, I don't mind. So it might be something, okay, which just quits sigma and may contain here a violation. Okay. So among deviations, you have also failure-free executions.
And you don't care about prefix?
Prefix, I don't care, because sigma is fixed. Maybe sigma contains failure, and I can talk about a deviation of a deviation, if you like. This I can. We can keep it. Is it fine with you? Okay. Clear for deviations? Because this is important too. Okay. So now this is the deviations of sigma. It means paths that are I deviations from sigma for some I. At some point you deviate. So with my definition here, I mean you may deviate here. It's no problem. Huh? So you just push this one. All right? So here's the logic.
So before you go there,
Wait.
why do you want something?
Sorry?
Why do you want something?
Why do I want something like this?
Yeah, you want to collect all the deviations in the sense.
Well, the thing is that to be able to quantify over, I mean, all possible, all possible ways of, say, changing the current path, right? By possibly having, I mean, one failure or less. That's what we want to capture. So we'll see through examples that.
So you're not really interested in identifying those branching points where the critical thing occurs.
Here?
Yeah. So if I think of this as a kind of a critical transition.
Mm-hmm.
So your interest is in identifying those critical transitions, or just to say there exists some.
Maybe I can tell you about the logic, what it wants to tell about, and we can come back to this. I don't know. Maybe this will answer. Right, so what do we have in the logic? So basically it's, as I said, you combine temporal operators with deontic ones. So first of all you have, as Guillaume showed already, you have the until next, so it will be interpreted over passes, full passes. You have the for all quantification. Let's say for all paths, blah, blah, blah. You have some obligatory, I will give the semantics, obligatory operator. And you have a quantification over all deviations, right? So this should be interpreted as robustly, for all possible deviations, something holds. This would be interpreted as pruned. This is a dual. And as you know already from deontic logic, this is quite standard. You have obligation and obligatory and permissible, the duals. So let's come to the semantics. So I don't know why I wrote all this. I mean, and I forgot the propositions. And this is very standard. I mean, proposition, you would get it from the valuation in the state. Next, you simply shift until standard for all. So here for all, you take any path that is just a full path. You don't require anything, but being a full path, starting as in the same state as sigma. This is the for all quantification for CTL star. It's very standard. Obligatory quantifies also over all paths that start from the very same state from sigma, but are concerned only in failure-free. So failure-free is the ideal world. It's executions where you had no problem. So, I mean, your obligation has to do with, I mean, what is conform to what conforms the norms. So this is a universal quantification over everything. This quantifies over failure-free paths, and this one quantifies over, I mean, deviations. All possible deviations, which may contain those that are not failure-free, as I explained. So those that contain, at most, one failure compared to the original path. So the thing is that here, you quantify over paths that may deviate from sigma, okay, at some point. So you quantify over, you start from the beginning, you quantify over all possible way of branching from sigma at some point, here or a bit later or whatever, but where, I mean, those would be obtained as, I mean, possible futures compared to sigma, but where at most one failure has occurred.
Why don't you care about more than one failure?
Sorry?
Why don't you care about more than one failure?
I will be able to
If a path has infinite number of
to
failures,
nest.
how do you capture it?
Well, by saying that there is a deviation of a deviation of a deviation by just nesting things. But I cannot say I have to count. I mean, I cannot say there is a finite amount of failures.
You are assuming that sigma is failure.
Not necessarily.
But when you say finite as opposed to failure.
I mean, compared to, I mean, no. One more failure than where I am.
But you are at sigma 0.
Yes, but as I said, I mean, if I had failure here, failures, huh?
But you actually have many other failures. So only if sigma is failure-free,
Let's say that, no, you're right. No, but you're right. I mean, the most, I mean, the way we will use it, indeed, is to first, I mean, consider sigma, which is, say, failure-free, and then deviate. The way we'll use the logic.
pi has exactly one failure.
Compared to, I mean, what's it, yeah. But you're right, I mean, no, but this is, you're right. I mean, it will be the way we use the logic.
Intuition of one, you have one failure every pi. The assumption is sigma is failure-free.
This is a better intuition. Yes, this is the right way to get the intuition. But, I mean, there's no point at the moment in enforcing this in the semantics. Voilà. But thank you, yes. Should have said it, actually. Okay for everyone? Right, so, and we can, lift the logic to states by saying that this should be a for all. This is a beautiful typo. One of these very late typos at night, during the night. So this is for all. So sorry about that. It's really... Okay, now let's come to examples. And then I will... Examples are much more interesting than the techniques we use, but I will tell you about the techniques. Okay. So what can we say about this? This is an example where, ideally you should help your neighbor eventually. Well, this is a statement. So normally, I would say for normal behaviors, you should help your neighbor. So you should eventually come to a point where H is, means you help your neighbor. This one says that you should, this is again what should be normal behavior, so this is obligation. You should, even if there is a failure, so we will see what it means. So if you don't help your neighbor, if at no point you help your neighbor, if you do not help your neighbor, you have to warn him. So I'll let you read a bit of this. So for example, there are things that are redundant. So we'll discuss this story about deviation. Now forget about the proposition V along computation, just think of this. So see for example this one. Just consider this formula. This one is redundant because this one says for all, normal behaviors, for all failure-free, if you like, or normal behaviors, this should hold. But you know also that for all normal behavior, f of h will hold. So trivially, for all normal behavior, if you do not plan to help your neighbor in the future, never, you will warn him. Why? Think of the semantics. This is for all failure-free behavior. Does this hold? Yes, it does, because for all failure-free behavior, this would hold. So implication with not f of h will hold. So for sure, this is redundant. But now here, in this second thing here, we have added something. So failure should be understood as, say, I do not conform to normal behavior. So if I do not conform to normal behavior, say, I have a behavior here where I will never, in the future, my behavior, so my path, the way I've chosen to, the policy I've chosen to stick to, is a policy here where, say, it violates this one. In that sense, it is a deviation. In that sense, it is an abnormal behavior. So it means that all along, it will not be the case that I will help my neighbor in the future. And this, in that case, if I'm outside normal behaviors, I want to be sure that then I warn my neighbor. Are you suffering? A bit?
The challenge is not to have the same obligation of operator to deal with these two level obligations, because usually that's...
Well, the semantics is perfectly clear. Either you conform to normal behaviors.
Yeah, it's the same with is that you like to have the same obligation operator which talks about the primary obligation and the contract duty obligation. And also I'm wondering, the violations can lead you to other things than when you have the for all delta.
The violation is due to the fact that you do not conform to what should be normal, those two statements.
Yes, but in general, the violations could be due to another voluntary obligation that
Well, it can be maybe this one. That's what you mean? I mean, as long as you say violate any obligation that you may list, you consider it as a deviation, if you like.
There are two questions. The first is the premise is the contract obligations to have the same obligation which deal with different levels of obligations. And here you have explicitly two different obligation operators.
Which one?
The first one, O, and then the second O and for all delta.
No. I mean, it's just nesting. O is O. I mean, I just have O.
Yes, but the thing, the challenge is to have the same O in both.
Well, this is the same O. I don't get it.
Because you have a for all, which says that because the obligation is variable.
I said that for all normal behaviors, so this is what Paul asked. I mean, we have a path with no violation. And for any deviation, okay, if I don't plan to help my neighbor, I do not help my neighbor if only if I warn him.
Yes, but the point is that the challenge is to avoid this, to have different kinds of obligation operators. To have this for all delta.
That the for delta should be inside the O.
So usually they have a sphere semantics.
No, but I mean, I just put it, I mean, it's inside this somehow. It's under the scope of O. That's,
The challenge is to avoid to have this.
we're perfectly happy. I mean, we can express a lot of things here. I mean, we have no paradox. But we can discuss this, of course. So something else I wanted to say. So about this OF, I wanted to say something that I've noticed. Yes. So if you plan not to help your neighbor in the future, so this one here, I would say that if lying about that fact that you plan to never help him is not conform to this one. So it means that as you would conform to this one, you would be like, say, I wanted to capture this morning and I didn't know how to do that. I wanted to say that if you plan to never help your neighbor, okay, so lying about that fact means that always promising, yes, lying, I mean, it's along the timeline. So if you plan not to help your neighbor, never. Lying about that fact, it means that always promising that the next day you will help, something like that. So saying, no, but not today, but tomorrow I'll help you. Tomorrow I'll help you. Indeed violates this first statement. Right? So it's about this. About this.
It depends how you specify your system. If lying is a failure, then.
No. Failure is about what is not conform to obligations. But I didn't introduce you're obliged not to lie, or I don't know. I mean, you come to a very complicated thing.
For the moment, you did not mention how you define failure in the system, how you place the
Because for the moment, I'm not at the level of structures and everything. I'm at the level of expressiveness for the moment. So I make it a bit like informal for the moment, what kind of things we can talk about. So this is a contrary to duty obligation. Okay, so you have a decision to commit to, P. The proper decision is P, not P is the wrong decision. Huh? So you should commit to the proper decision. So it means that, I mean, it's obligatory that, okay, you have one step to make your decision. At the next step, you commit to the proper decision. So you always, I mean, take P as a decision. So this is, you should commit to the proper decision. And then it says that once you have made the decision, done, you should stick to it. So either you made, I mean, the good decision, P, or you made the wrong decision, not P. So this says that after you've made a decision, you should, it's obligatory, I mean, you should, this is normal behavior, you should stick to it. So either in the future, you stick to not P because you've made the decision not P, which is the wrong one. This can be understood as a failure, say. And otherwise, you stick to P. Okay? So imagine you made the wrong decision. If you can make the wrong decision. This is completely, I mean, consistent with I mean, you should, but this tells you about what should happen or not what really happens. So if you make the wrong decision here, when you've made this decision, okay, we cannot satisfy this because the other one says that you should stick to your decision. Okay, so it means that you should stick with the G not P. So it means that those are both true. Can you see why? This comes from here. Oh, this is no. And because you have made the wrong decision, then this holds. But you made the wrong decision. Actually, well, this holds because you stick to not P. And on the other side, I mean, those are not true. Is it clear? So just looking at this tells you that now if you change phi into GP or G not P, whichever you want to show, it is very important to see that how obligation and things along time just change. I mean, it's not because you're obliged in the next state to do that, that in the next state you're obliged to do that. Because indeed, I mean, decision may change what becomes obligatory. So this may also be what you think about certifying. I don't know. Okay, so we can make it with generals, and if you're interested, I can show you coordinated attack, whatever. If general 1 commits to an attack, then it cannot withdraw. So you have all kind of things like this, all kind of statements, and we show that. I mean, if we assume that there is only one failure, so it means that when somebody sends the message, it doesn't arrive. Okay, we can add other constraints, which are about like once general G2 receives plans, he will send 2 messages, one message, next time one message, and then commit to attack. Because we have in mind that we're going to take as an assumption that there is only one failure, it can be generalized. And then you can infer that the policy we've given is consistent by being able to decide satisfiability and so on, which I will explain. And we can also show that, I mean, the normal behaviors tells you that if there is at most one failure, you would come to a point where both commit to attack. These kind of things we can do. Feed the cat. That's another story. Well, we can show that, I mean, again, if there is only one failure, there is a policy how to feed the cat so that the cat never starves and so All right, so I just I skip. So I call it the bit flipper, but it's flipping bits also. Okay, so let's now have what? 20 minutes, less actually, because we want to discuss. To give you a flavor of things. So first of all, it is by simulation invariant. This you can expect. Why? Because it's very easy, because things are encoded with propositions V and so on, to see that if you take two bisimilar things, you have a path, okay, which is a failure. You have two paths that are bisimilar. This you can always find, because if you take a path in one structure, bisimilar to another structure, you get bisimilar one where point by point are bisimilar. You take a deviation of one, you can obviously easily get a deviation from the other one so that they are bisimilar. Okay? And this is enough to show bisimulation invariance or by induction over the formulas. Because if you state for all deviations or there exists a deviation, you can, I mean, both sides, for the two bisimilar things, you can rebuild the objects that the logic tells you about. Super easy. So now we come to QCTL star. So QCTL star is like CTL star, very simple. This should be an X. This is typos again. So next, I've changed my notations, but I didn't have macros before. But you can also quantify here. So what is the meaning of this? Imagine this is a CTL star formula. You can evaluate this CTL star formula on a tree, infinite tree. This will be the semantics. I mean, we will feed only with trees. And now you can say that there is a way, I mean, whichever way you put proposition P. So let me think. I take a tree. I say that T prime is a variant of a P variant of T if T prime is just like P. But maybe if you change the way proposition P labels the nodes. The states, the nodes, yes, of the tree. So a P variant of T is simply the same tree, but P is put differently. That's it, right? So you would say that a tree in a node satisfies for P phi star if for every P variant of T, this formula holds. Maybe you would be, I mean, much more happy with the existential quantification. So I have a tree, and I wonder if there is a way to put proposition P somewhere so that some formula holds. Think of exist. It's much more easy. Is there a way to change my way of putting P along my tree so that phi holds? Like, for example, eventually P, for all paths eventually P, it's easy. I take P, I put a frontier of P proposition that I must cross along any branch, and then I come to a way to put P so that for all paths eventually P.
The point is, then the semantics is, it's sort of independent of where you are in the tree, right? Because you're going to look at variance of P for anywhere in the tree, right? That's why.
Yes, but then you evaluate in the same node.
You evaluate in the same node, so you're just concerned about, I mean, the subtree. I put X. So it's just a way to tell this. The way I will use it is very simple. If I tell you for all P, if J of P, for all P, J of P implies something.
Sorry.
Yeah.
That's okay. You evaluate the formula in the same form, right? But you change the evaluations down in the future, all over the place.
Well,
So
that's, you can do arbitrarily. It's very weird, but look, I mean, yes, but the way I will use it is like this. If I write something like this, blah, 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 if I have a tree in a node satisfying this, it means that, for example, this is, I mean, very, very comfortable. I'm here. I can put P in such a way that actually it gives me a path. So this for sure will hold if I take a single path and not P everywhere else. Okay, so I can say that whichever path I take, something holds. It's some way to quantify over paths. because that's the minimal objects you can get that satisfy everywhere P. And it should also hold for this way of putting P. So this is the only thing you have to keep in mind. Because it's next, I said, I forgot, it's typo, it's X, next. That's all. Okay, so it's decidable, non-elementary, this is very standard. And let me show you just precisely what we do. So first of all, I will convert my CTL formula, QCTL star formula, into another one, okay, which says that, so if you think of the deviations, if I have a path, now I say that for all paths starting from it, such that at the next step, there is no violation. So it means that it is a deviation but failure-free. This is what it says. So this now is changed into for all paths, which is failure-free, I must have phi star. This is what it says. So it is simply something to say that if I happen to say that obligatory is something, I can simply turn it into in QCTL star, even for the moment in CTL star, I simply can quantify over those passes where at the next step I don't have the failure, and because afterwards I'm failure-free, it means that it is a failure-free deviation. That's the intuition. So if I, yeah?
When you have a next in your formula, I thought that the O modality was for all failure-free passes.
It is for, and this is to simulate it.
But here you allow for, no, okay, because there cannot be a failure.
It doesn't, it's meaningless.
Okay.
Just need to. So it's a way to simulate the O quantification. That's all I should say. And the other way to simulate, so we can simulate the O quantification with, CTL star, and now I'll show you how to simulate there exists a deviation such that, and not the for all, which is much, it would be the dual, but it's easy to explain the exist. So there exists a deviation such that blah, blah, blah. This I can also simulate in QCTL by saying, okay, so let's look at this here. So this formula says, if I take a path, basically, for a path, there exists a path that is either the very one, so this is your GP, either the very one, this path. So imagine this one denotes sigma, P, here. So either there exists a path which is either this one where phi star holds. One possible deviation is itself, the path itself. Otherwise, it's something else. What is this something else? It is something here where whatever happens here, I don't know, but let me think where I am. Yes, here there exists a path such that eventually that will be the point. I do one step and one step, and remember this one is failure-free. Failure-free. So either I do two steps, so I come to a point, which is this I for the deviation. I come to a point where P holds, so I'm still in here, and after two steps, 1, 2, I'm failure-free. So it's a deviation of sigma with at most one failure. Okay? So either you have a path which is itself unsatisfied, psi star, or there is a deviation with at most one failure, and it satisfies phi star. So this simulates the quantification. There exists a deviation where phi holds. You can simulate it in QCTL star. That's the idea. So with all of this, you make a translation which is very, cheap, because you can see that those ones do not explode in the formula. You add a little bit, but it's not too bad. So what you get at the end is that because you know how to translate, this is the correctness. You may also ask that, this gives you I would say, a way to translate. And if you want to say that phi is satisfiable in the ROCTL star structures, you simply add what ROCTL star structures should be like. So it means that there exists failure-free passes in the structure, and you simply decide whether this is satisfiable. It is QCTL star, so you can decide the logic in the frame. Okay? Drop. So now the very challenging part. I didn't expect to take so much time. So I give you just the roadmap. It's very nice. There's no need to know more, so I will tell you about this slide, another one, and I will be done. If we want details, I'm going to have other slides that I can show for questions or whatsoever. So the roadmap is the following. First, you define this thing, which is basically something like this. LTL plus counter-free finite state automata. The semantics is like the semantics of LTL, but if you want to know whether a path satisfies I, you want to say that there exists a prefix which is accepted by this automaton. This is the meaning of ALTL. And you require all automata here to be counter-free. Why? Because I will obviously obviously, the trick is to make this logic, you will see where it is convenient here, to make this logic translatable into LTL. So if the pieces I put inside the automata operators I add to LTL are counter-free, I can use, all knows about it, the result that tells you that any counter-free automaton finite word can be translated into an LTL formula. So this is reasonable. Then I can attach to any formula here an automaton. This automaton is a bit weird. It's a step towards this one, which says that basically this one accepts a path. A path, say, if only if this path has a deviation that satisfies alpha. This we can do. Then it becomes clear that, with all the constructions here, I will be able to simulate all operators in ROCTL star into this one, plus new propositions, because I have CTL star to deal with and not LTL. So when I come to state formulas of CTL star, I just put kind of propositions for the moment. You know, this is the techniques for model checking CTL star on top of the model checking of LTL and so on. Then what you can do is, because you have this ATL thing plus some propositions, you may re-inject all these things in a full CTL star formula that is equivalent to, so let me show you the theorem. This is a bit complicated. Voilà, it's here, down here, forget about this. This is the first translation here, and now what you do is that you take the formula that you have built in this very weird intermediate language. It contains some, you see, if I say for all phi, I translate it in this logic with a proposition that say for all, not phi of course, but the meaning of this with its translation into ATL. It's not very surprising. But now, when I want to translate a formula from here, I do it by first taking its translation here and replace all these propositions by the formula they denote. So you come to some, so you replace any proposition of this kind with a proposition here. And as you have in here automata, this simulates the existing deviation satisfies alpha, because you say either myself, I do satisfy alpha, or I am accepted by this automaton which says that there exists a deviation of mine which satisfies alpha, which is exactly the meaning of this quantifier. So the construction are very nice, but so this gives you a way to translate into CTL star. So the main idea is to say, look, I have to tell about deviations. I do it, with the help of automata. And you have all things like those automata are, if alpha is taken in here, this automata is also counter-free. So this automata counter-free can also be translated into LTL-like stuff, and everything works well. It's about checking that everything remains counter-free, which is enough. Right. Now the last thing is about optimality. So there is also a very beautiful proof, which is the following. So we want to show that there is no translation of ROCTL star into CTL star that would be elementary. So non-elementary stuff comes from the fact that, I should have said it, that in here you duplicate formulas. You have an explosion, okay? Each time you cross some quantifier over deviations, you duplicate. Okay? So it will be non-elementary, it will be kind of k plus 3 exponential in the depth of quantification over deviations, but not alternating. The very right number of nested deviations, quantifiers over deviations. Not a matter of existence for all. But, now, so the translation would be if you take a formula which has, say, maximal nesting depth of deviation quantifiers k, you would get a k plus 3 translation of what we have. And we show that, you cannot do better, essentially. So the proof is very nice. It's just to tell you about techniques that are standard. So here, in that case, we go through this roadmap. So first of all, you define trees, parameterized by 2 integers, a height, and a number of bits per label on the trees. It's a class. So you have this beast. And it can be established that the number, this number, of pairwise non-isomorphic such trees, is non-elementary in H. Okay, so you have a non-elementary function that is non-elementary in H, that gives you, given H and L, how many isomorphic classes you have. Then we can build a structure that actually results from, you take a prefix of T and you glue a suffix of T prime here. So you can have such structures, you can define them, and you can build an ROCTL star formula, this one, which accepts such gluing as long as the 2 trees T and T prime are isomorphic. So there is a formula that is able to characterize those glued trees somehow, for which, which are based on 2 isomorphic pieces of gluing. Isomorphism. No. Are they unranked? Yes, maybe. No, I don't know. It's the proof of team, so this is why I do not detail. It must be unranked, maybe. So then,
if it is an unranked tree, then even with steps with height 1, you have infinitely only non-isomorphic unranked tree.
with step 1, but if I fix L, if I fix L, I'm stick with.
If it is an unranked tree with height 1, so in order to have the level in place and the number of bits per level,
Ouais.
I can think of non-dissimulation. Then indeed,
But if you.
replication doesn't help. So I think
But the labels, I mean,
Makes sense for me.
so if
With my simulation.
here you would say by simulation
There's
trees.
non-simulation equivalent trees, something like this. But instead of non-isomorphic seems very strong.
Yes, sure, but
If they are rough, then it's unclear to me that you get so many non-elementary seems to be to me if they are rough.
But I mean, why do you say that already with height 1 you get,
In round 3, you can have as many children as you want.
right?
And 2 trees with a different number of trees.
Oh, no, okay. No, I see. Okay. And if I take the, but if I take the, if you take the, if you question by simulation,
It's non-isomorphic. It may make sense if you say non-by-simulation equivalent.
well, okay then. No, okay. Then this must be,
By-simulation
I mean, non-isomorphic canonical representation of those things. So it's,
It's plenty of by-simulation. Anyway,
no, I agree that for unranked, I mean,
your logic is by-simulation.
wait.
So
It comes much earlier with, I mean, being able to compare ROCTL star with the tree semantics of QCTL star and stuff like that. But, I mean, here also, I mean, but, so the non-isomorphic should be thought of as a base simulation, up to base simulation. Right. So, I mean, to conclude, at least, if you happen to be able to do that with ROCTL star formula, then, I mean, what you may need to, if you had an automaton, say, that would represent this formula, the automaton must, I mean, give enough information to, I mean, to be able to, I mean, while reading the prefix T of this gluing, it should be able to, I mean, of course, remember enough information to know, I mean, which class T belongs to. So it should have at least, I mean, be able to distinguish at least that many different equivalence classes. Then this gives you somehow a lower bound of the number of states that the automaton should have. And now, because we have elementary translations from CTL star to automata, I mean, it is not the case that we can have an elementary translation from RCTL to CTL star. Then we would go to an automaton which has an elementary amount of states. Okay, so the last things, of course, is that there are elementary fragments. I mean, there are things where translation to CTL star is not too bad. So, for example, if you just nest, some of the constructions can be, I would say, optimized if you have n-nested operators, quantifiers, but not broken by obligation or for or things like that. If they're just consecutive ones, you may have optimized way of translating. And this is the kind of things like there are at most n failure. So to quantify over passes with at most n failures, okay, the deviation of a deviation of a deviation. This gives you 3 failures. So this is reasonable in a practical point of view. Because the formula here only uses this, it's important to understand that the problem doesn't come from, as I said, alternation between quantifiers of a deviation. So it's not a matter of alternating depth of quantifiers. It's a matter of well, something else that we have to better understand. And of course, I mean, for the moment, we have no clear lower bounds for deciding ROCTL star. I would be happy to, sorry about time, discuss this with anyone here. Construction and whatever. Okay, so thank you.